In this video, we'll go through Einstein's derivation of the A and B coefficients for stimulated and spontaneous emission. We'll first start by reviewing transition probabilities. Then we'll derive the Einstein A and B coefficients. And finally, we'll get an expression for the spontaneous emission coefficient. So the probability of stimulated emission, and of course of absorption of radiation, in a two-state system depends on the perturbative Hamiltonian, which is h prime is equal to minus the polarization P times E sub 0, which is the magnitude of the electric field, times cosine of omega t, where the polarization is given by a polarization vector is equal to Q times the inner product of psi b r vector psi a. If you have an electromagnetic wave perturbation with a frequency omega naught, that's at 0, the probability of stimulated emission is given by P beta A of t is equal to E sub 0 squared over h bar squared times the modulus of the polarization squared times sine squared of omega 0 minus omega quantity times t over 2 divided by omega 0 minus omega quantity squared. While the transition rate of stimulated emission from incoherent unpolarized light with the distribution rho omega sub 0 is given by RBA is equal to pi over 3 epsilon naught h bar squared polarization modulus squared times rho of omega sub 0. And this is clearly a constant times this polarization distribution rho of omega 0. Now, Einstein didn't have the benefit of quantum electrodynamics to derive the proper rate for spontaneous emission, which is really stimulated emission from incoherent radiation in the vacuum. He was able to calculate the coefficient of spontaneous emission using what was known about quantum mechanics at the time and any experimental evidence to perform this calculation. And he used the reasoning that this coefficient for spontaneous emission had to be related somehow to the coefficient for stimulated emission. So the way the derivation goes is the following. You start with the goal of developing a connection between the three coefficients that you have, the absorption and emission, both the spontaneous and the stimulated emission coefficients. And you do this by imagining a system with n atoms. N sub a of them are prepared in the lower state psi a, and n sub b prepared in the upper state psi b. We want to now construct an expression for the rate of change of the number of atoms in state B. So it's dn sub b dt. And that has three components. The first is the reduction of that number due to the spontaneous emission rate. This is what we eventually want to calculate. We'll call that minus n sub b, the number, times the rate of spontaneous emission, which is A. Then we have a reduction due to the stimulated emission, where stimulated emission, again, it's proportional to rho of omega sub 0, and it has some coefficient b sub ba. And so this becomes minus n sub b, b sub ba times rho of omega sub 0. And then finally you have the increase due to the absorption, and we know that the absorption then will give you n sub a, the number of particles that are in the lower state, times the transition probability b a sub ab times the density of radiation rho of omega sub 0. And this has to be equal to 0 if you're in, this whole sum has to be equal to 0 if you're in equilibrium, where there's no change in the number of atoms in state B. Well, we can just rewrite this then as n sub b times a is equal to rho of omega sub 0 times the quantity n sub a, b sub ab, minus n sub b, b sub ba. If we then divide through by b sub ba over here, and then divide everything by this quantity, you can get an expression for rho of omega sub 0. So rho of omega sub 0 then becomes A times n sub A over n sub B times BAB minus BBA. Sorry, you divide by n sub B. And this is then our expression for the density of radiation at omega sub 0. It's equal again to A over n sub A over n sub B times BAB minus BBA. So the relative number in the two states we know is given by the Boltzmann distribution in equilibrium, because thermodynamics has to hold. And Boltzmann distribution tells you the relative numbers of these two populations. And that is dependent on the temperature and the energies. So it's n sub A over n sub B is just equal to e to the minus e sub A over k sub bt divided by e to the minus e sub B over k sub bt. We can then combine these two exponents to get e to the EB minus EA over k sub bt. And that's the ratio n sub A over n sub B. And we obtained this from thermodynamics, and we can plop it right into this expression. One more step before we go there is we realize that this energy difference is simply h bar omega sub 0. So we can rewrite this as e to the h bar omega sub 0 divided by k sub bt. You can then calculate the photon density of field density at omega sub 0 by substituting this quantity in. And that becomes rho of omega sub 0 is equal to A over e to the h bar omega sub 0 over k sub bt times BAB minus BBA. If we now look at Planck's expression for black body radiation, which was well known at the time that Einstein did this derivation, rho of omega is equal to h bar over pi squared c cubed times omega cubed over e to the h bar omega over k sub bt minus 1. So by comparing these two, you can extract information about what BAB, BBA, and A would be. So the fact that these two are so similar forced Einstein to postulate that the rate of absorption, BAB, is equal to the rate of emission, which is BBA. So if these are equal to each other, then you can just replace this with A over BAB. And then you can calculate, with this correspondence between these two expressions, you can calculate what each of these coefficients is. BBA, which is the rate of stimulated emission, is equal to pi times the polarization modulus squared divided by 3 epsilon naught h bar squared. And A is equal to omega sub 0 cubed over h bar over pi squared c cubed times B sub AB. If we then substitute B sub A, BA in there, you get that A is equal to omega sub 0 cubed times the polarization modulus squared over 3 pi epsilon naught h bar c to the third power. And this now is the spontaneous emission coefficient A. You can notice that it has some similarity to the stimulated emission coefficient here. It has the same units of the polarization, and then it has other units here that will give us an exact dimensionless coefficient.